Howdy folks, this is a walkthrough for Lab 9, so the second part of our automation exercise in Petzold's Chapter 17. This will take us up to page 209 in your Petzold text. So he mentions at the bottom of page 219 that they're going to make, we are going to make a fundamental and excruciating change. Well, we're not going to make that fundamental and excruciating change until the next lab. So this lab we're going to finish up the Harvard architecture to make fully capable 16, 24, 32-bit, whatever adding machine. Right now we just, at the end of chapter 8, we just had an 8-bit adding machine. We don't have a way to store the carry out from a previous operation, which means we can't do anything bigger than 8 bits. So we're going to modify our arithmetic logic unit, or ALU for short, in order to do that. Right now our ALU consists of these two things, the selectable inverter and the adder. And we don't really have enough room on our main circuit page to add a bunch of things right here, so we're going to break this out into a different circuit. So first thing you'll notice in the lab is it says, let's take out our these two things, our ALU, and make a new subcircuit called ALU. So remember, right click on your lab, let's give it a name, and on my main circuit I want to select my selectable inverter and the adder, and I'll put these in my ALU. So we're going to need a few inputs. One is, if you look at the main again, we need something from the data RAM, and we need something from the accumulator. So two of those data inputs. I want to make that 8 bits. Copy paste using Control-C, Control-V. Alright, and also we're going to need a subtract signal, so let's add a 1-bit input for subtraction. With the flag. Okay, and then an output. Nope, sorry, this is output, or Control-5. And that needs to be 8 bits. Alright, let's make a picture for it. I think 6 by 10 is going to turn out to work pretty well for us. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Close enough. That's our subtraction. That's our second data input. And output. I don't want to turn this upside down. That'll be our clock once we have it. Okay, so now I think I'm ready to put this into our main circuit. Just click once on ALU. That's going to be in the wrong place. so the output needs to go to the multiplexer. One data input from the RAM, and the other from the output of the accumulator. And this is our subtract. So let's see. Alright. So let's see if we can do what we could before, if we have the same functionality as before. So let's load 3.3 and add. Is that add? No. That's add. 2.2. Now we'll store the result here and stop our program execution. No. Oh. Load. Store. Alright, let's try that again. Okay, now we get 5.5. That looks good. Now if we subtract, let's try 5.5. So 2.1 is subtract, I think. So now let's run through that, see if we get 3.3, and we do. Alright, so so far we have the functionality that we did at the end of Lab 8. The only thing we've done is we've broken out our ALU. Okay, so this second part says now we've got to add the ability to store our carryout into some latches. So we're going to need some extra control signals. And where I got this from was the technical addendum to Petzold, which you'll see a link in Sakai. But he says, oh, you just add this. And so basically we're doing this, except I found it didn't exactly work, and I'll show you why it didn't work. I actually had to add a second latch. There might be a way to do it without adding a second latch using rising and falling edges of a clock, but just to keep it at least what I think is easier, I added a second latch. So that's, if you're wondering where it came from. This is my implementation of the control signals listed in Petzold's technical addendum. So the first thing that we might talk about is how we need to change the subtract signal for our carry operations. Because now there's going to be besides subtract, there's subtract with borrow. So let's add that. Carry and a regular add. What else? Oh, we need a clock. Yeah, I'm just looking at this right now. Reset. Let's add some tunnels. everything. Yeah, so looking at this picture now, it looks like we've got to add some registers for our carryout. So those are going to be 1-bit registers, and you can find them in the memory section. So 1-bit, using Rising Edge again. It's not the accumulator. This is actually called the Bucket Brigade, from the days when, if you wanted to put a fire out, you had to have a guy at the well with a bucket, and then put a guy next to him with a bucket. The guy from the well puts his water into the second bucket, and the guy in the second bucket puts his water into the guy standing next to him with the third bucket, and so on until you get to the fire. And it takes a while to fill up all the buckets, but once you do, you get a decent flow rate going. So this is the same idea, except for storing information in a serial way. So if you want to store 2 bits in this set of registers, first you put the lowest order bit in the first register, then you hit the clock. What's in this bucket is going to go into that bucket, and what's in the output of the adder will go into the first bucket. So you end up filling both registers. It just takes 2 clock operations. So that's a way to do it serially, as opposed to the way we've been making our latches in the 8x1 RAM array, for example, which was in parallel. Okay, so we've got some resets here, and our clocks here. All right. So now, besides the subtract operation that will require us to invert this input, there's going to be another, well, I'm just going to actually copy this one. We also have to invert our input for subtract with borrow. So either of these options this thing is just terrible for somebody with OCD. Okay. Oh, jeez. Anyway. All right. And what else is true? We also need to invert the we need to carry in for both of those. All right. Now what else am I missing? Oh, right. So, okay. So also we're going to need to carry in, but we don't need to invert it if what am I saying? If we have an add with carry operation. So there's 3 situations where we're going to need to have that carry in be something. These 2, but now also if I don't want to do this. Yeah, I don't want to connect those 2. Let me see. there's a better way to do this. Yeah, the problem is if I connect these two, then every time I get a subtract or borrow, I'm going to necessarily have that carry in, which is not what I want. Alright, the third option is if I have an add with carry. So we're almost there. The only problem is, here I've said that I want the carry in to be 1 if I have an add with carry operation. But that's not always going to be true. Unlike subtract, where this carry in always needs to be 1 because I have to have the 2's complement, which is all of the bits inverted plus 1. I don't actually want a carry in with my add with carry operation, unless there happens to be a carry out. So unless there happens to be something from this line, I don't want this. So what we need is an AND that feeds this. So it's going to be 2 input AND gate. Alright, I think I have this now. Yep, that looks good. So yep. Okay, now we have one problem yet to fix, if you're wondering what all this garbage is down here. I want to add my carry out. And the problem is, let's say that we want to add a number that has a carry out. So I have an add operation. Right now the answer is 0 with a carry out of 1. So this is 128, that's 128. When I add them together, I get 512, which is 1 in the 512's place and 0 for the rest of the sum. So if I wanted to add another, add the higher order bit now, I would, first I need to cycle the clock to store the carry out bit in this latch. Now I want to add the higher order bit together. I want to add a higher order bit with a carry operation. So let's say that that is going to be 0 and 1. Just want to add 0 and 1 together. I want a 1 from the last carry to be added to this, so I really want a 2 as my output for the higher order bit. So let's cycle the clock again and see what happens. Nice, I got a 2 because 0 plus 1 is 1. Added together with the carry out from the previous operation gave me a 2. What happens, the reason why this might not work, let's reset everything, is if I do exactly the same thing, now I have my carry out from the previous operation, but the next thing I want to do is I want a store operation. So I'm going to cycle the clock for the store. And now I want to add the next two numbers. I want to load the next two numbers. So I load a number into the accumulator, I cycle the clock, and then I do an add with carry operation. Oh, shoot. Okay, here's what it was. Yeah, I forgot to load my higher order bit. So yeah, now if I store that, I'm cycling the clock. And then if I load another two numbers, I cycle the clock again. Look what happened to my carry. It's long gone, right? So we really don't want the clock to advance this bucket brigade unless we use one of these four operations. So that's why we do all this stuff. So here, let me add some lines now. Make this the inputs to a 4-input OR gate. Okay, so now the clock signal will be sent if we advance the clock and one of these four operations is enacted. So now it should work. And I think we need to modify this a little bit. Yeah, this mess. So this is our carry out. I'll put it up there. Subtract with borrow, I think is here. Reset. That's the second input. Let's add with carry. It looks like add. That's the clock. This is subtract. Let's make this a little bit bigger. Something like that. Okay. Add with carry, subtract with borrow. Okay. Yeah, every time you change that picture, you have to go back to your main circuit and make sure things still match. And that's our subtract, which is here. Yeah. This is shoot, our instruction decoder. Yeah, okay, so this isn't going to work until we change our instruction decoder. So in the lab, this is actually a step 2, which I skipped. So let's go ahead and do that now. We're going to modify our instruction decoder to add a couple more opcodes. The first thing I want to do is move this. There's a little more room. Some people used 8-input NOR gates with all of the inputs inverted. That's totally fine. We're going to just did the AND because, I don't know, I'm lazy. So first I want to do add with carry. And add with carry is going to have opcode of 2-2. So let's see. This is 2 for the first, and that's 2. That means I'm going to need to invert the third and the 7th. 3rd and 7th. Okay, that looks like that works. I don't like this, I don't know what, yeah, so to fix that, alright, next subtract. Subtract with borrow is 2, 3. So that's 2, 2, 2, 3 is just one more bit here. So I want to invert this line, 7th over. It's called subtract with borrow. Okay, let's see what the picture looks like. Oh god. It's good to have the inputs 3 apart here because that's how wide the tunnels are. Right, so just want to make sure I have them all in order. No. And that's good. That's not good. Yeah, okay, perfect. Alright, so now we'll have to go back to our main again because we moved these things around. See, load, that's good. Store, that's good. Add, that's good. Add, that should be add with carry. Which is that line. And then subtract, which is that line, and subtract with borrow is that one. You can leave the tunnels in there if you want, just as labels, or you can take them out. You're going to need store, load, and halt, but you don't need to have tunnels for add and subtract and add with carry and so on. What's this one? Add. Problem. Okay. And I want to add a carry out. 1 bit. And then I have some clock signal going in here. Let's see. That's this. And reset here. Woo! Alright, let's try it out now. Let's try the same thing where we're just subtracting 5, 5 from 2, 2. And hopefully we'll have a 3, 3 stored in that address. So reset to set my program counter back to 0. And I do get 3, 3. Now if I want to subtract is 2, 2, I believe? No, 2, 1. Oh, that is subtract. If I want to add, that's 2, 0. 7, perfect. Okay, so we have the same functionality as we did before, but now let's see if we can add two 16-bit numbers together. And I thought maybe the easiest way to demonstrate that was with this slide. So this is the easiest example I could think of where there was a add with carry operation. So the lower order bytes have 8s in them, so there's going to be a carry, right? It's going to be a carry of 512 plus 1, and then the higher order byte is just 1 plus 0. So I just want to make sure that when we're done we get a 2 here because there's going to be a carry from this operation, and this addition is just going to result in a 1 because we have 0 plus 1, which is 1, and then these two give us an overflow into the next label. So let's try that out. Let's see, load. First I want to do the lower order byte, which is an 8-0. And I want to add that, just a normal addition. Let's make sure I have my codes right. Yeah, okay. So add is 2-0, and we're adding 8-1. And then I want to store that result in this. You can leave that whatever it is. Now I want to load the higher order bytes. So higher order bytes are 0, 1. And then I'm going to add with carry. 2, 2. Yeah. So I'm going to add 0, 1 and 0, 0 for my higher order bytes, and then I want to store that result here, and then stop the program. So what I hope is that we get 0, 2 here and 0, 1 here. So let's try that out. Let's reset. Good. I'm happy because this is the add line, which is lit, and my carry out is lit because when I added my 8s together I got a carry out of 1, and the result should be 1, which isn't yet stored in the accumulator, but there's 1, 1 for store, and that result gets loaded into the third byte. Now I'm doing another load operation, so I'm loading a 0, 1. I'm adding that to 0, which should be 1, except since there's a carry out from the previous operation, I hope correctly, that there's a 2 now, which will get stored on our next operation. Okay, so it looks like our add with carry is working correctly. And all you have to do for the rest of the lab is just put in this program and make sure that you get the A9 and CH like he does in the textbook. Okay, that's all for the walkthrough. If you have any other questions, please call or text.